Every pilot must have a working knowledge of the principles of aerodynamics. This aerodynamic awareness began during your initial training, when, as a student pilot, you gained an understanding of the fundamentals of flight. However, as you progress through your flying career, you should continue to gain knowledge in this area so you can truly understand, apply, and correlate these concepts to everyday flying. The primary emphasis of this video is how the angle of attack affects various aspects of flight. In addition, we'll focus on correlating the aerodynamics of angle of attack to stall and spin considerations, and look at some basic aerodynamic formulas. Aerodynamic discussions typically stem from conversations of the creation of lift and the relationship of the forces acting on an airplane. However, in order to better understand these forces, you must be able to measure and calculate them as they apply to aircraft in flight. The pressure differential between the upper and lower surfaces of a wing is the catalyst of any lift analysis. This pressure differential multiplied by the planform area determines the wing's aerodynamic force. Although this seems to be a logical place to begin a discussion concerning a wing's capabilities, changes in the angle of attack and velocity alter the direction and magnitude of the aerodynamic force. This makes it difficult to correlate aerodynamic force to aircraft performance. A better way to predict performance is to simplify the analysis of aerodynamic force by dividing it into two components: lift, which is perpendicular to the relative wind, and drag, which acts parallel to the relative wind. With this goal in mind, let's take a closer look at lift and how total lift and, consequently, aircraft performance are determined. To fully understand lift, you must first analyze the various factors which affect it. A simplified form of the lift formula states that lift is a product of the coefficient of lift times the wing area times 1/2 the density of the air times the velocity of the relative wind squared. You should note that the density of the air portion of the equation represents static pressure, which is the force of a stationary air mass. When 1/2 the static pressure is multiplied with the velocity of the relative wind squared, the resulting constant is dynamic pressure. If any of the variables change, total lift as well as aircraft performance is affected. The coefficient of lift is determined by the airfoil's shape and angle of attack. It's simply the ratio of the dynamic pressure generated by the wing to the surrounding static pressure. This value measures how efficiently a wing converts dynamic pressure into lift. The coefficient of lift value derived for each angle of attack is determined by wind tunnel tests, where all of the other variables in the lift equation are known. They range from 0, where no lift is being generated, to approximately 1.6 in typical cambered airfoils. To more easily understand this concept, the values can be plotted on a graph to show how a change in angle of attack alters the coefficient of lift. Let's first look at a symmetrical airfoil, where the curvature of the top surface is the same as that of the bottom. This graphic shows that a symmetrical wing's mean camber line coincides with its chord. Since the velocity of the airflow around the upper and lower surfaces is the same at 0 angle of attack, the result is no pressure differential. This means that the symmetrical airfoil produces 0 lift at a 0-degree angle of attack. As the angle of attack of a symmetrical wing is increased, the coefficient of lift can be plotted on a graph. The value increases steadily as the angle of attack increases until reaching the maximum coefficient of lift, or CL max. Beyond this point, the coefficient of lift drops suddenly as the wing stalls. Symmetrical wings are usually associated with aircraft designed to fly at high subsonic or transonic speeds. They are also effective on airplanes that require positive lift during inverted flight. Returning to the graph, the same type of curve is drawn to represent a cambered wing's coefficient of lift versus angle of attack relationship. Unlike the symmetrical design, the cambered airfoil produces lift at a 0-degree angle of attack. High camber designs increase the lift coefficient for a given angle of attack. This wind tunnel demonstration shows that the cambered wing must be at a slightly negative angle of attack before the paths of the airstream over the top and bottom creates zero pressure differential, or a zero lift coefficient. It's quite easy to see the effects of camber on lift by watching an aircraft with a short takeoff and landing design. STOL aircraft use a highly cambered wing to generate high lift coefficients at relatively low angles of attack. In addition to showing how an increase in angle of attack results in an increase in the coefficient of lift, up to CL max, the graph also shows a correlation between angle of attack and velocity during straight and level flight. You can plot several airspeed values along the curve to show that as the airplane slows during wings level flight, the angle of attack must increase to maintain altitude. Referring back to the lift formula, you can see that there are only two variables that are pilot controllable. First, by varying the angle of attack, you govern the coefficient of lift. In addition, you can normally regulate the velocity of the relative wind by changing your power setting or flight path. As we expand on the formula, lift is shown to be directly proportional to the square of the velocity. For example, if you double the velocity, lift increases fourfold. This means that an airplane flying at 150 knots experiences 4 times the lift as it does when traveling at 75 knots, as long as the other factors, including angle of attack, remain constant. However, if you double your velocity without changing the angle of attack, the airplane tends to climb if trimmed for a slower speed. Therefore, in order to maintain altitude and balance the forces in a state of equilibrium, you must decrease the coefficient of lift as you increase velocity. As the graph shows, you normally lower the coefficient of lift by lowering the angle of attack. You can experience this by trimming your airplane for cruise flight. Then, with one hand on the control wheel, increase power and maintain level flight. The control pressures tell you that the airplane wants to climb. This confirms that an increase in velocity causes an increase in lift at a given angle of attack. While the relationship between angle of attack and airspeed is fairly constant in level flight at a given weight, significant changes occur when the flight conditions vary. Aircraft weight, maneuvers, and configuration alter this relationship. At a given airspeed, a heavier airplane requires a greater coefficient of lift to maintain altitude. This increase in lift is supplied by either a higher velocity or an increase in angle of attack. If you don't apply additional thrust or it is not available and the critical angle of attack is exceeded, the airplane stalls, regardless of weight. An example of this is an airplane at full power. As additional weight is added, the only way to increase the coefficient of lift is to increase the angle of attack. In an attempt to maintain steady flight as weight continues to increase, you'll eventually exceed the critical angle of attack at a full power setting. This graph supports this relationship. For example, a 10% increase in weight results in a 5% increase in stall speed. A 100% increase in weight increases the stall speed by over 41%. This is exactly what happens in a 60-degree constant altitude turn, where the airplane's weight is doubled by the 2G load factor. These statistics help you see the need for avoiding steep turns at low airspeeds, a flight condition common in stall spin accidents. This typically occurs when pilots overshoot the turn from base to final, then tighten the turn to align the airplane with the runway. In addition to knowing how changes in the angle of attack alter the coefficient of lift, you should understand how total lift is influenced by high lift devices. For instance, as you extend flaps in preparation for landing, you increase the maximum coefficient of lift and reduce the angle of attack for any given lift coefficient. This increase in CL max reduces your stall speed since more lift is generated at a given angle of attack. You can determine the actual stall speed mathematically through this equation, which states that the flaps down stall speed equals the stall speed without flaps times the square root of the maximum lift coefficient in the clean configuration, divided by the maximum lift coefficient with the flaps down. For example, let's say your airplane stalls at 50 knots at the landing weight with the flaps retracted. Assume that the maximum coefficient of lift, clean, is 1.5, and the maximum coefficient of lift with the flaps down is 1.9. A simple calculation shows that by lowering the flaps, your stall speed is reduced to 44 knots. Now let's return to the lift formula to analyze the variables that you cannot influence. The first is the density of the air, identified by the Greek letter rho. The density is measured in slugs per cubic foot. A slug is a unit of measurement wherein the weight of a cubic foot of air is divided by the acceleration of gravity. As the formula expresses, lift varies directly with the density of the air. Simply stated, the more dense the air, the more lift produced. Because the density of air decreases as you gain altitude, you must fly at a greater true airspeed at a given angle of attack to maintain altitude. Otherwise, the wings cannot generate enough lift. Likewise, the same holds true on hot and humid days. Assuming that density does decrease, either the angle of attack or airspeed must increase to provide sufficient lift, or the total weight will exceed lift and the airplane will descend. Although it is possible to directly control density by adjusting your altitude, it's obviously an unrealistic way to govern lift as you maneuver the airplane. The final variable in the lift formula is the wing area. Lift varies directly with the wing square footage, provided the planform does not change. This means that a wing with a planform area of 200 square feet produces twice the lift at the same angle of attack as one with only 100 square feet. That's why you'll find that airplanes with short wings typically have high camber to increase the coefficients of lift at lower angles of attack. Now let's look at how angle of attack influences total drag. Since drag, like lift, is a component of the total aerodynamic force, the drag equation is the same as the lift equation, except the coefficient of drag is used instead of the coefficient of lift. Therefore, the force of drag is the product of the coefficient of drag, dynamic pressure, and wing surface area. The coefficient of drag is simply the ratio of drag pressure to dynamic pressure. It portrays how much dynamic force is transformed into drag. Since drag is normally an undesirable characteristic, manufacturers attempt to minimize the coefficient of drag, meaning that efficiency is measured when dynamic pressure is converted into small amounts of drag. When plotting a typical drag coefficient curve, you can see that the coefficient is low at low angles of attack, and small changes in the angle of attack produce slight changes in the drag coefficient. However, at higher angles of attack, small changes in the angle of attack create substantial changes in drag, especially as you near a stall. When analyzing the curve, it's important to understand that the coefficient of drag starts at a value greater than 0, since there is always some resistance to motion. Although the lift and drag curves portray their relationships to angle of attack, it's easier to understand performance considerations when the two curves are plotted together and the lift-to-drag ratio is examined. You can now see that as you increase the angle of attack, the lift-to-drag ratio increases to a maximum, and then decreases at the higher lift coefficients and angles of attack. The graph makes it easy to show that the LD max occurs at one specific angle of attack. When flying in steady, unaccelerated flight, this is the precise angle of attack where total drag is minimized. Any higher or lower angle of attack reduces the lift-to-drag ratio, and subsequently increases the total drag for a given amount of lift. While this information is important to airplane manufacturers for determining performance criteria, it's also very significant for pilots, since the LD max provides for the best power-off glide ratio. This ratio represents the amount of horizontal distance traveled for a specific amount of altitude lost. For instance, let's assume this airplane has a glide ratio of 8:1, meaning that it can produce 8 pounds of lift for every pound of drag. At this ratio, for every 8,000 feet you travel horizontally, you will lose 1,000 feet of altitude. During a power-off glide, the distance traveled is the same regardless of weight, provided the LD max angle of attack is sustained. Since most light airplanes do not have angle of attack indicators, manufacturers list the best glide speed which corresponds to this angle of attack. Often, only one speed is listed in the POH, since the range of possible weights is rather narrow. Therefore, small deviations from the optimum coefficient of lift will not cause a drastic reduction of the lift-to-drag and glide ratio. On an aircraft with a wide range of weight possibilities, the manufacturer might list more than one speed. This is because as weight increases, the speed required to maintain the LD max angle of attack also increases. We can demonstrate this by looking at two airplanes of different weights during a power-off glide. Since the glide ratio is based only on the relationship of the aerodynamic forces, the airplane with the greater weight needs greater lift. If you attempt to generate the additional lift by increasing pitch, the angle of attack increases above that for LD max, and you will not achieve the optimum glide ratio. Therefore, the added lift can only come from an increase in velocity. Notice that the forward component of weight for the heavier airplane is larger than that on the lighter airplane. When the correct speed for LD max is maintained, this difference causes the heavier airplane to fly at a higher velocity. The increased velocity also increases the drag force, so the opposing forces remain in equilibrium, and both airplanes maintain the same flight path. Although the heavier airplane goes faster and descends more quickly, the horizontal distance is not affected. From this discussion of LD max, you should be able to correlate what would happen if you attempted to stretch a glide, if it appeared you could not reach the landing area. Although the natural reaction would be to increase back pressure, the increase in angle of attack above LD max would ultimately increase the glide angle and decrease the horizontal glide distance. Another flight situation that will reinforce the lift-to-drag relationship is the landing phase of a flight. Let's take a look at some of the procedures performed during a landing and see what aerodynamic implications they might have. As you extend the first notch of flaps in preparation for landing, the initial deflection produces noticeable changes in lift without generating large changes in drag. As you continue lowering the flaps on base and final, both lift and drag increase. These higher coefficients provide you with a lower stall speed and steeper descent angle. However, flap deflection beyond approximately 50% of the flap range produces a greater change in drag than lift. Now, drag has a greater influence on the airplane than does lift. After applying power for a go-around, you must adjust the flaps to the manufacturer's recommended setting, since the drag generated by full flap extension produces a drag coefficient that outweighs lift. If the flaps are not set properly, the airplane's climb performance is well below its maximum capability. In extreme cases, it may not be able to climb, or may continue to descend, even with full power applied. To wrap up our aerodynamic discussion, let's shift gears slightly and take a look at the basic aerodynamic considerations of spins. As you probably already know, the airplane must exceed the wing's critical angle of attack and stall before a spin can develop. Often, one wing will drop in a stall and the nose of the airplane will attempt to yaw in the direction of the low wing. If the yaw is allowed to continue, the airplane slips toward the low wing. As it does, the air hitting the side of the fuselage, the vertical fin, and other vertical surfaces tends to weather vane the aircraft into the relative wind. This accounts for the continuing yaw which is present in a spin. At the same time, the airplane is rolling around its longitudinal axis. This is caused by the descending wing having an increasingly greater angle of attack due to the upward motion of the relative wind. The coefficient of lift and drag curves show that the descending wing has a greater angle of attack than the rising wing. The descending wing suffers a tremendous loss of lift since it's well beyond the critical angle of attack. On the other hand, the rising wing is producing comparatively more lift because the relative wind striking the rising wing is at a smaller angle. This means that this wing has a smaller angle of attack and therefore is producing more lift than the lower wing. Remember, beyond the critical angle of attack, a greater angle of attack means less lift. At the same time, the descending wing encounters a greater coefficient of drag than the rising wing. The combination of forces creates a continuous rolling and yawing motion called auto-rotation. The airplane descends vertically while rolling and yawing until recovery is accomplished. During the recovery process of most general aviation aircraft, the ailerons should be neutral. If aileron is applied in the direction opposite the turn, the chord line changes and actually increases the descending wing's angle of attack, amplifying the spin. Aileron deflection in the direction of the spin may alter the spin characteristics by increasing the rotation rate and changing the pitch attitude. It's also important to apply rudder opposite the direction of rotation. This allows the relative wind to strike the vertical tail surface, thereby reducing the yaw. Once rotation slows, brisk forward movement of the control wheel should break the stall. One of the key aerodynamic elements of a spin is the effect of aircraft loading on recovery. Since the airplane spins about its vertical axis, a forward CG provides a responsive rudder, since the rudder moment is long. However, as the center of gravity moves aft, the moment decreases, and rudder effectiveness is reduced. In extreme cases, the rudder may be ineffective in arresting the yawing motion incurred in a spin, making it impossible to recover. Although you received basic aerodynamic instruction during your primary training, the value of a more comprehensive understanding becomes apparent when you apply aerodynamics to everyday flight. By arming yourself with a broader aerodynamic awareness, you should gain a better understanding of why the aircraft performs as it does, so you'll be less likely to fly beyond the aircraft's limitations. The following presentation provides samples from our flight time programs. Jeppesen-Sanderson's Flight Time Video Series, the best source of aviation knowledge for the serious pilot. This videotape contains samples from our extensive flight time video collection, covering subjects like weather, Jeppesen charts, instrument procedures, and multi-engine operations, as well as a number of general interest aviation topics. Choose the topics that interest you most. Our weather subjects feature information on weather hazards, sources and methods for obtaining weather briefings, making an informed go, no-go decision, resources for gathering and evaluating in-flight weather, and the hazards of aircraft icing. Here is a segment of weather hazards.
Let's turn our attention now to another source of wind shear. Beneath convective clouds lurks the most dangerous form of low-level wind shear, the microburst. In extreme cases, it can produce downdrafts in excess of 6,000 feet per minute and horizontal winds of 120 knots or more. This can occur in an area as small as 2 miles in diameter.
Our 3-pack of Jeppesen chart videos is applicable to experienced veterans and newly rated instrument pilots. It covers approach and route and SID and star charts. Here's a look at a sample from SIDs and stars.
Before we take a close look at how the Altum 5 departure is flown, let's look at the aircraft performance required to guarantee obstacle clearance. An obstacle-free flight path is based on your aircraft climbing at 200 feet per nautical mile after it crosses the end of the runway at least 35 feet above the ground. In addition, you must be able to climb to 400 feet above the airport elevation before reaching a point where a turn is required. A slope of 152 feet per nautical mile is assessed for obstacles. If none penetrate this slope, the 200 foot per mile gradient provides you with a minimum of 48 feet of obstacle clearance for each mile of flight. If obstacles do penetrate this slope, special avoidance procedures are specified.
Our instrument topics include programs covering practical tips for flying in instrument conditions, as well as important information on emergency situations. Here's a look at a portion of IFR emergencies. In addition, if you lose two-way communications while IFR, you should fly at the highest of the following altitudes or flight levels. The last assigned altitude. The minimum altitude, which is usually the minimum en route altitude or other charted minimum altitude. Or the altitude ATC has advised may be expected in a further clearance. Remember, you must fly at the highest of the three altitudes specified for each route segment being flown. Our multi-engine program is an excellent tool for initial instruction or review of multi-engine operations. It is also the perfect complement to Jeppeson's multi-engine manual. Here's an excerpt from the multi-engine pilot program. The best single-engine rate of climb speed, VYSE, sometimes called blue line airspeed, has several applications to multi-engine flight. It gives you the best rate of climb, or the slowest rate of descent if you can't maintain altitude. Another application of VYSE is in connection with the single-engine service ceiling. This ceiling is the maximum density altitude at which VYSE will give you a 50 foot per minute rate of climb with one engine inoperative. The single-engine absolute ceiling is the maximum density altitude an airplane can reach and maintain on one engine. Now that we've discussed the theory of engine-out flight, let's look at some practical applications. Running on Empty is an exciting soaring video featuring world champion sailplane pilots competing at the Masters of Soaring Invitational. Actor and soaring enthusiast Cliff Robertson narrates this program.
He's been the envy of man for thousands of years. The Indians think of him as the messenger to the Great Spirit, the transcendent symbol of flight whose beauty and grace has inspired within us a longing to fly with him and beside him, to share his spirit, his dominion, and his freedom. In emulating much of the eagle's symmetry and harmony, man has resolved his yearning to soar.
In addition to these specific subject areas, we also have a number of programs available covering general subjects. They include such areas as aerodynamics, physiology, flight in high-density traffic areas, night flying, and VFR emergencies. Here's a segment of From Dusk to Dawn. The hours between sunset and sunrise can offer some of the most enjoyable flying you'll ever experience. Not only are the skies less crowded, but the air usually is smoother. However, flying at night can present many problems for an inexperienced pilot or one who hasn't flown at night for some time. So it's important for you to occasionally review your night flying procedures and limitations. Jeppeson's Flight Time video series is a convenient and stimulating way for you to refresh and expand your aviation knowledge.